factory assembles calculators. Each calculator requires a chip and a battery. It is known that 1% of chips and 4% of batteries are defective. So you need two things happening, chips and batteries. So we can go...
Miss, I have a question. How do you know? I know we use tree diagrams here because it says tree diagram.
Because it's a multi-stage event, because there are two possibilities, two things that... Oh, just let me record. But yeah, because there are two things here that could... Either the chip is defective or not, and either the battery is defective or not. So that's a multi-stage event. There are two things that need to be considered.
But it's multi-stage.
Yes. So for multi-stage events, tree diagrams are for multi-stage events. Now that includes rolling dice twice, tossing a coin 3 times, or tossing 3 coins at once. First coin, second coin, third coin. Getting tickets in a lottery or something. First ticket, second ticket, first prize, second prize, third prize. So every time there's a different event that happens, you need to draw a tree diagram. So I'm going to go defective, not defective. So if there's a 1% chance, probability that 1% are defective, so what do I put on this branch? I can put 1% or 0.01, and on the other branch, not defective, I get 99%. Now, see, whether the chip is defective or the battery, they don't have any bearing on each other. Okay, they don't, it's not like one will affect the other, all right? So they're mutually exclusive events. So, again, battery, not defective, defective, not defective, defective. So what have we got for batteries being defective? So we got 4% defective, 96% not. Can you see that really well? It's not the best pen. And again, 96% not defective, 4% defective. So we've got not defective, not defective. I could have just put N. Not defective, 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 not defective, and defective, defective. Now, it says, so that's our tree diagram. It is known that 1% of chips and 4% of batteries are defective. Find the probability that a calculator selected at random will have at least one defective component. Probability of at least one defect. At least one defective. Isn't it the ones that I'm circling? That one? That one? That's right. And that one. Instead of working those 3 out, isn't it just 1 minus the probability of no? Wait a sec. I've made a mistake there. Isn't it these 3 that they're talking about? Yeah. Probability of at least one defective. These, that, and that. So it's everything except for that one. Probability of 1 minus no defects. So it's 1 minus probability of ND, which is 1 minus, now how do we do this probability? We multiply, we do, now 99% is 0.99, can we write it as that? Yeah. 0.99, and 96% is 0.96. So 1 minus 0.99 times 0.96. I mean, you could work out the probability of no defects first, okay? Now, you probably should give your answer as a percentage. So get your answer, because the question, you should actually, the question probabilities are given as percentages, the answers need to be, so just get your answer to that. What's 0.99 times 0.96? So 1 minus 0.9504, which is 0.0496, which is what percent? Yeah, to change a decimal to a percent, you multiply by 100. Now, yeah, and I think it's easier to make them into decimals and then convert back at the end, all right? So probability of at least one defective is 4.96%.
But is that what you do for all the questions?
Yes, you need to do each time there's an event, you need a separate branch of the tree. Notice that the probabilities, 99% and 1% adds up to 100%, or 1. Yeah. 96 and 4 adds up to 100, 96 and 4 adds up to 100. Let's just do a couple, okay? 4 canaries, 5 cockatoos and 3 budgerigars if 2 birds are selected at random. So what I would put up the top is bird 1. The first bird that's selected could be what, or what?
Canary, cockatoo, or
Canary,
budgie.
so a C-A, a C-O, or a B-U. A C-A, a C-O, or a BU for a budgerigar. That's bird 1. And then bird 2. Now, there are enough. A CA, a CO, or a BU. It's going to be big. A CA, a CO, or a BU. Or a CA, a CO, or a BU. Now, you need to put your probabilities on the branches. Now, we've got 4 out of what? So, total is 4 plus 5 plus 3 is 12 birds. So 4 out of what? Keep it, don't write it as a third, all right? It's 4 out of 12. Keep it as 4 out of 12. If you start simplifying probabilities on the branches, you're never going to be able to fill out the next branch. You're going to make it so much harder for yourself. And then CO, cockatoo, is 5/12. And is this big enough, girls? And the budgerigar is 3/12. These numbers, there are 4 canaries, 5 cockatoos, and 3 budgerigars. That gives me 4 plus 5 plus 3, 12 birds. The chance of picking the first bird, you got 4 out of 12 chances of getting the canary. Do you get it? Now, no, do not simplify. Definitely do not. Now, if you took a canary out, how many canaries are left? 3 out of how many birds? And now, did you take a cockatoo out? No, 5 out of 11. Budgerigar, we didn't touch that. 3 out of 11. Get the idea? So I've got 1 less canary here. The next one, canaries, there are still 4 out of 11. Can you see, girls? Cockatoo, well, we took 1 out. How many for the cock? 4 out of 11. Budgery, 3. If 1 budgery's gone, there's still 4 canaries. There's still 5 cockatoos. And there's 2 budgies left. Little budgies. So, all right, girls.
Cockatoo and canary have
C-O-C-A. I'm putting the A first. So probability of canary. No, it's 4. You go along the branch. Here's no, we've got 4 out of 12 times CACA. What is it?
No, 3/11.
Times 3 out of 11, which is, well, you can simplify. Is it 1/11?
It's 1/11. Well,
Yeah.
that's the answer I got.
Yes, because the 3 cancels with the 4. Right, 1 on 4. The 4's cancel. All right, probability of 1 canary, 1 cockatoo. You got the CA first, then the CO, or, which means plus. So girls, 1 canary, 1 cockatoo is that one or this one. Can you see it can happen 2 ways for part B? So part B, and that was part A, that one. Oh yeah, sorry. I missed it. Can I just do it? Part C, sorry, is 1. All right, this is A. Oh, geez. Forget labeling them. A is probability of canary. Sorry, C is 1 canary, 1 cockatoo. You can have canary first, then cockatoo, or cockatoo, then canary. So plus cockatoo, then canary. Along the branches, we multiply. Between the branches, we add when it's or. I could have this situation or that one. So the ones with the dots is C. So what have we got? Canary, 4/12 times cockatoo, 5/11 plus cockatoo is 5/12 times what? Canary, 4/11. Girls, you're going to get the same thing for both. Numerators are both 20, denominators are both 132. So it's 20 over 132 plus 20 over 132, which is 40 over 132, which I think they're both divisible by 4.
Wait, why'd you skip me?
Because I missed it accidentally.
Oh, so you haven't found it yet.
Yeah. So what do we get? Someone help me, please. 10 over? All right, I'll just slow down. Are we good with that? There's a canary. The first branch, just ignore it. That won't be any of those. You've got CO, 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 BU, BU, CO, BU, BU. So because it's that or that or that or that, remember multiplying along the branches, adding between the branches. So it's that. If you want, I'll write or. Do you want me to write or not? All right, remember plus means or, plus means or, plus means or. Plus, what's CO? 5/12 times 3/11 plus BU, 3/12 times 5/11 plus 3/12 times 2/11. So girls, the denominators are all 121. Just add your numerators. What do you got? 20 and 15 and 15 and 6. Girls, do not do it on your calculator. Do not even think about doing it on your calculator. You know why? Because by the time you enter it, you've lost about a minute. Girls, these are really easy numbers to do. 12 times 11, sorry, I've got that wrong, is 132. All right, check that one. But please, girls, denominators are the same. It's 20 plus 15 plus 15 plus 6. Shh. Girls, I'm done. Eddie Maguire. Who wants to be a millionaire? The person lost how many thousands of dollars on that? I'll have to find it. 30, 50, 56. Now you can get your calculator out.
It's 14 on 33.
So if you want to check 12 11s if you have to, please, 20 and 15 and 15 and 6. Write them out and add them. Next, D. At least one.
This is where we minus.
Yeah. At least one means one minus none. At least one, CA canary. 1 minus the probability of.
No. There's only 2 of them. Oh, isn't it? No way.
No, you just did them.
Yeah.
1 minus the answer to part B. 1 minus probability of no canaries, which is 1 minus the answer to part B.
19 on 33.
Yep, which is 19 on 33. Good old canary. Question is question 18. It says 2 dice are rolled and a 3 appears on at least one of the dice. So we know we've definitely got a 3. And one of the other numbers is something else. So girls, how do we do our tree diagram?
Dice 1 and dice 2.
Well, yeah, first dice, yep, dice 1 and dice 2. It's a 3 or not a 3. That's what I'm going to do for this one. Because, oh, but it doesn't have, stop, doesn't have to be that. Mistake. Start again. Do you want to do a grid?
Yeah.
I think so. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Otherwise, look, the other thing you could do, girls, is, all right, let's try it. You can see what you got, girls. Just fill in the ones you want. Don't do the whole lot. What do you need? 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6, 3. Do not do the whole lot. What else do you want? This row. 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, 3, 6. I wouldn't do any more because you'll be there forever. Now, the sum of the uppermost faces is greater than 7. Just one sec. We've got to, I'm circling them, but I'm going to do it another way as well, all right? Before I finish off that, I think this looks okay, 4 out of 36, but I'm going to do it another way as well. So probability that the sum is greater than 7 is 4 out of 36 possibilities, 1/9. No. So it's not right. I'm going to do it another way. No, but we don't know that it's already on the first one or the second one. So I want to do it another way. I'm not sure if that's right. I was really having doubts with that. So you've either got a 3. Wait, no, let's do a 3 and then it has to be a what? 5 or a 6. Or you could have a 5 or a 6 and then a 3. Now I think, see, I'm really worried about that way because that's throwing, just, no. 2 dice are rolled, no. You could get a 3 on the first die or a 5 and a 6 on the second. Now what's the probability of getting a 3 just on its own? I want to do a diagram too. So this is the other thing I want to do, leave that. So couldn't we get a 3 and a not 3, but then we want a 5, 6 or a 4 or a 1, 2, 3, 4. If you, wait, or a 5, 6, or a 1, 2, 4. Look, I'm just trying something. I like this. You can get a 3 on the first dice, couldn't you? And you'll need a 5 or a 6. So what's the probability of a 3 just rolling 1 dice? 1 out of 6 times. What's the probability of getting a 5 or a 6? 2 out of 6. Plus, you could have got a 2 out of 6. A 5 or a 6 is 2 out of... So just think, if you're rolling it, how could this physically happen? A 3 appears on at least one of the dice. I don't know if this is going to work. Wait. Times 1 on 6. So we want a 5 and a 6, then a 3. Is this going to work? 2 out of 36 plus 2 out of 36. I'm getting the same as that one. Right. Just ruined that one. We were on the right track here, and we're going to come back and look at this again. But because there must be a 3, so would we go, I'm just going to try and, wouldn't you have 1 then times? If there has to be a 3, yeah, it's only these that are the possibilities. You've got 4 out of 11. I'll have to delete that bit of the video. All right, probability of a sum greater than 7, but this is now your sample space. It's 4 out of 11. How would you do it this other way? All right, we're done. 4 out of 11. Because, because this has to be my sample space. One of them is definitely a 3. If you were to do it this way, there's not a 1 in 6 chance of a 3. That was a definite. I think it's 1. And this is a 1. And that doesn't work. 4, 6, 2/3. Forget that one. That doesn't work. Forget all that. So it's that. 4/11. Oh, interesting one. Very good. Very good. The reason you have to just use these is that one of them has to be a 3. So all those other elements that aren't drawn in the grid are not in the sample space. It says at least 1 3 appears. So like the 1 4 is not even included. It's only these that I can look at, because you have to have at least 1 3. Got it? So that's why it's 4 out of 11. 22. It says in each game of sick bow, 3 regular 6-sided dice are thrown once. I can't do a 3-dimensional grid. In a single game, what is the probability that all 3 dice show 6? So you're not going to do a grid, it's fine, just use numbers.
It's just 3 dice.
Probability of 6. I don't like writing that. Repeat. I'm not writing the number of the beast.
Isn't it 3 out of 12 times 3?
6 times 3. No. It'll be 1/6 times 1/6 times 1/6. Because just think, if you've got a tree diagram, you want either they're all worried about sixes or not, whatever. Like you've either got a 6 or not 6. Do you know what I mean? 6 or not 6. Girls, sometimes, ladies, with tree diagrams, if you did want to draw them, is that 1 over 216? All right, girls, sometimes with tree diagrams, if you feel you need to draw them and it's a dice, you don't have to put 1, 2, 3, 4, 5, 6. You can go 6, not 6. All right? 6, not 6. 6, not 6. It's sometimes easier. And then again, 6, not 6, etc. So if you want the probability of 3 6s, you can see it's a 6 times a 6 times a 6. Remember, multiply across the branches. Now the next one is exactly 2 6s. Now, actually, I don't mind this diagram. Well, I'm just going to put this in without all the... So if you want, if you want exactly 2 6s, maybe the first one will be a 6 and the second one, but not the third. See, you could have probability of a 6, 6, and then not 6. Do you see that? So the first two could be a 6, but not the last one. What else could you have? Maybe the first one's a 6, then not, but then yes. In other words, girls, the last one's not, the second one's not, or the first one's not. You can occupy 3 positions. Or, now plus means or, you could have not 6, but then 6, and then another 6. Does that make sense? If you've got 2 out of 3 6s, either the 6s will be in positions 1 and 2, 1 and 3, or positions 2 and 3. The not 6 will either be the last one, the middle one, or the first one. So therefore, what are those probabilities? A 6 times a 6 times 5, 6. Aren't the others all going to be the same? You'll get the same. Look, a 6 times 5, 6 times 1, 6. We'll just do it. Plus 5, 6 times 1, 6 times 1, 6. In other words, it's 5 out of 216 times 3. Because I get 5 out of 216 plus 5 out of 216 plus 5 out of 216. What would the denominators add up to, girls? If it's 5 out of 216 plus 5 out of 216 plus 5 out of 216, what is it? 15 out of 216. Does that make sense? Or 5 out of 16 plus, it's like I'm saying 2 plus 2 plus 2 is 2 times 3. 5 out of 216 plus 5 out of 216 plus 5 out of 216 is 5 out of 216 times 3. 15 out of 216, which is 7. They're both divisible by 3. What do you get? Got it? So girls, this is really good. So with a dice tree diagram, we don't want every number. 6 or not a 6. Got it? Probability, now this is different. But, girls, why can't this just work with every other number as well? What is the probability that exactly 2 shows 6? Well, you could have 2 6s, 2 5s, 2 4s, 2 3s, 2 2s, and 2 1s. So, girls, the probability of 2 6s equals the probability of 2 5s, etc., which equals the probability of 2 4s, do you get it, etc. So therefore, it'll be, therefore the probability of 2 of the same is 5 out of 72 times 6. Because you need that, that's for 6, and then you need the 5 and the 4 and the 3 and the 2 and the 1. There are 6. So times 6, or 5 on 72 plus 5 on 72 plus 5 on 72, because I need the 6s, the 5s, the 4s, the 3s, the 2s.
I don't know how much times you find 6 and not 5.
Because, don't I want 6 of those?
But we already, that one's already for the 6.
All right. Just one. 5 on 72 plus 5 on 72 plus 5 on 72. You would add this 6 times, wouldn't you? That's for the 6s, the 5s, the 4s, the 3s, the 2s, the 1s. Which is 30 out of 72. So it's, guys, just be careful. Guys, do we get that? That's part C. These are good questions. All right, D. Probability of rolling 3 different numbers. I have a feeling we need D, the probability of 2 different numbers. Girls, 3 different numbers. It's 1 minus probability of 2 the same minus probability of 3 the same. Now, we've done probability of 2 the same already. Well, we've done all 6s the same.
So then we just
Times that one by 6. So it's 1 minus the answer to part C. So 1 minus the answer to part C minus 6 times the answer to part A. Because part A is 3 6s. But then you could have 3 5s, 3 4s, 3 3s, 3 2s, and 3 1s. So it's 1 minus 5 twelfths minus 6 times 1 on 2, 16. Are we good? So it's 1 minus answer to, imagine trying to work them all out. It'd be a nightmare. So that's part D, probability of 3 different numbers. So it's 1 minus 5 twelfths minus 1 on 36. Well, that's 15, 16 on 20 on 36. Divide that by 4. Lovely. In your head. You can do it if you want, but don't worry. This one you're allowed to use a calculator for. All right. Are we good, girls? These are good questions, really good questions. Just like the sock question, okay? You know the sock question? Doesn't matter what the first number you picked was. So the probability of rolling 3 different numbers. Doesn't matter what the first one is. Have you got 5 out of 6 for the next one? No. 4 out of 5. One number's gone. 5 out of 6. Yeah, there's still 6 on the die. Okay. So first number, doesn't matter what you get. Second number, let's say you got a 2. You could get anything but a 2 next, which is 5 out of 6. Remember the die still has 6 numbers on it. We're not pulling balls out of a hat. All right, and then the next one, you're allowed 4 other numbers. So that's 20 out of 36, which is 5 out of 9. But with that, you've got to be really careful here with this first one. You have any number first, it doesn't matter. All right? So that's really like, that's bringing in your perms and coms knowledge, I think, like it, sort of. Sort of, not, so, it's not perms and coms as in perms and coms, but it's like it doesn't matter what's there first, okay? As long as the other 2 are different. All right? So that's one way, and that's fine too. All right? Just go for this if you're really sure, this second alternative method, all right? Otherwise, the other one's a bit safer. But you've got to be very clear here, all right? A set of 4 cards contains 2 jacks, a queen and a king. I think we can go like this, jack, queen, king. There's only 4 cards. 2 out of 4 are jacks. 1 out of 4 is a queen and 1 out of 4 is a king. So a set of 4 cards, there's only 4 cards, not 52, contain 2 jacks, a queen and a king. Bob selects 1 card and then without replacing it selects another. Be careful, because if he gets a jack, how many jacks are left? 1 out of 3. How many queens are left? 1 out of 3. How many kings are left? 1 out of 3. But if he selected a queen first, what's left? If he selected a queen, are there any queens left? He's only got jacks and kings. How many jacks? 2 out of 3. How many kings? And if he selected a king first, there's no kings left. There's just a jack and a queen. 2 out of 3 and 1 out of 3. Okay. So, probability that they're both jacks, that's fairly okay. Are we good, girls? 2 over 4, leave it as 2 over 4 times a third. What's that? It's a half times a third. A half times a third.
2 on 12.
Yeah, 1/6. B, at least 1 is a jack. Do we know?
Is it a 1 minus
Probability of J, no.
at least?
Oh, yeah, good girl. 1 minus,
Everything that's not a jack.
yeah, at least 1. But there are lots. Oh, no. At least 1 jack. Oh, yeah, we'll do that. Equals 1 minus no jacks, which is 1 minus, which ones?
2K
1 minus QK
and KQ.
and probability of KQ. Yeah, otherwise you've got to add up heaps of them. So probability of at least 1 jack would be that, and that. Too many to do. 1 minus, what have we got? A quarter.
Times 1/3.
You only do brackets if you're going to add them.
Yeah, as in like brackets around.
I like to do brackets around this and that. You mean here?
Like 1 minus bracket.
If you're going to add them, yes. So you either take them away both individually or you add them together and then take the total away. So QK is a quarter times a third and KQ is a... Wait. No, it doesn't. No, times 2 KQ. So it's just 1 minus 1/12 minus 1/12. Isn't it? Which is 10/12. Which is 5/6.
What is the last question you asked?
Given that at least one of...
Say at least.
Given that one. C. Given that one of Bob's cards is a jack. He picks one up and then picks another. In other words, you're only allowed to work with this branch. The rest of the tree diagram is not relevant here. Given that one of his cards is a jack, so don't even bother that it's 2 out of 4, because that's a given. One of the cards is a jack. What's the probability that the other one is also? It's just a third. No, because you're supposed to pick a card out and then pick the next one. So this is definite. It's just like in the question before we said...
So it's 1 times a third, which is a third. Yeah.
Yeah.
His guess is 1 of 5.
All right, just one sec. Oh, yeah. We've got to look at some others. So we've got this. The other one is also... All right, I know what's... Oh, all right. Or we go work that out. Oh, we did all these. At least 1 jack. So, 1 minute.
He's sure, but Miss, isn't that the same as the first question?
No. Our sample space is that, JK, and this. The other 2 are not part of my sample space. They don't get included. So, given that one of Bob's cards is a jack, the other one is as well, we've got 5 choices. The others are obsolete, just like that dice question. But because you've got numbers on the branches and each of these is not equally likely, it's not. If you work out the probability for each of those, it's different. So you need the probability of jack-jack over the probability of all of them. So it's the probability of jack-jack over the probability of all of them, which is the answer to part B, over the probability of at least 1 jack, which is your answer to part B. So that's the probability of jack-jack, which we did in part 1. It's a 6th over 5/6, which is a 6 divided by 5/6, a 6 times 6 on 5, 1/5. Definitely correct. Okay, girls.